Hey guys, this is Professor Janacek, and I want to go over how to find double integrals in polar coordinates. To begin with, you might want to review how to change between polar and rectangular coordinates back from trigonometry or pre-calculus. What's going to happen in this situation is our region is going to be defined instead of in x's and y's, it will now be defined in terms of r's and thetas. So let's take a look at how that will play out. So to begin with, I'm going to take one of our little rectangles. Remember, this is our region over which we are integrating. I'm going to take a look at one of those rectangles and just kind of enlarge it here. So we'll take a look at that. Now, if you recall, we'll have our change in the radius. That's delta r. That's going to be one dimension of this. The other dimension, if you recall how to measure or how to find the arc length in polar coordinates, that was r times theta. So you'll notice I have r naught times theta on one end, and on the other end, on the other side of this rectangular-like figure, we have r1 times the change in theta. So how in the world do we determine dA? I do want to point out first off that dA is not equal to dr theta. Right? We have to think about how to find kind of almost like the area of this rectangle-like figure. So to begin with, I'm going to just suppose that r naught and r1 are approximately the same value. This can be achieved because we're going to take the limit as these two guys get really close, and so at some point we can just assume that they are the same. So we'll simply call them both r. Now, what about the change in our area? The change in the area, again, if we look at this, it's going to be kind of like as if this were a rectangle. It's going to be the change in width. So that's delta r times the change in length. Right, the change in length there. The change in length is either r naught delta theta or r1 delta theta, but since those r1s and r naughts are the same, it'll be delta r times r delta theta. Which of course I'll turn around, I'll write that as r delta theta. And so this is how, again, technically these are approximations, but this is how we'll write dA. dA, as we take the limit of the delta A, we'll end up with r dr d theta. So again, notice that dA is not simply dr d theta, it is instead r dr d theta. Right? Make sure you remember that dA in polar coordinates is r dr d theta. Very common for people to leave off that extra r there in the front. All right, so let's take a look at how we'll find those areas. Again, f is a continuous function. The region below it is defined by r theta, where r goes from a to b and theta goes from alpha to beta. I do want to also point out that the difference between alpha and beta is always going to be less than or equal to 2 pi, so it's not that we always have kind of those smaller angles. All right, so if we have a double integral over r of f, we'll simply write that as the double integral from alpha to beta, and then from a to b of f of r theta, r dr d theta. Again, don't forget, this is r dr d theta instead of, oh dear, that should be dA back here. dA, there we go. All right, well, let's dive in and take a look at an example. I think the hardest part about these examples is making sure you understand what things look like. Here we have example 1. We want to find the volume of the solid that's below z equal to 4 minus x squared minus y squared. Recognize that this is a paraboloid, and it's above the region r going from 0 to 2 and theta going from 0 to 2 pi. I have sketched that out. Again, this is the paraboloid here. And a paraboloid opening down, the top of it's up at 4 on the z-axis, but it goes all the way down to the xy plane. All right, so if we want to find the volume here, that is the double integral over r of, now originally we thought of this as a function of x and y and then dA. So realize that in this situation, take a look at all this. In polar coordinates, x is equal to r cosine theta, y is equal to r sine theta. So that's going to be the function in terms of r cosine theta, well, in terms of r and theta, instead of x's and y's. And then, of course, dA, we know is r dr d theta. So how do we set up this integral? Well, another thing to notice is that my function is the z value. So in this case, f is z, which is 4 minus x squared minus y squared. But we want this in terms of r's and thetas, not x's and y's. So that gives us 4 minus x squared plus y squared, which is 4 minus r squared. So we'll take the double integral of 4 minus r squared times r dr d theta. Now I will go ahead and keep this in the order of r and then theta, integrate with respect to r, then integrate with respect to theta. You could change those if necessary, but that usually will integrate with respect to r first and then with respect to theta. So the limits of integration for theta are from 0 to 2 pi, and r goes from 0 to 2. So if we integrate with, actually let's clean this up a bit. Let me go ahead and distribute that r, so we get 4r minus r cubed dr d theta. Integrating with respect to r gives us 2r squared minus 1/4 r to the 4th. We'll evaluate that from 0 to 2 and then integrate with respect to theta. Evaluating that, actually, I'll let you guys take a minute and go through that. Let's see, that should end up being, again, take your time with that. Feel free to write out as much as you need on this. That gives us, what, 8 minus 4 minus, of course, 0 which is just 4 d theta. Oh, that's an easy one to integrate. That gives us 4 theta, evaluated from 0 to 2 pi. Let's see, evaluating that from 0 to 2 pi gives us 8 pi. Well, there we go for the first one. Not so bad. Let's take a look at the second example. We want to find the volume of the solid bounded by z equal to 2x squared plus y squared and z equal to 27 minus x squared minus 2y squared. Again, these are also paraboloids. Notice that z equal to 2x squared plus y squared is a paraboloid sitting there on the origin or the pole opening up, whereas z equal to 27 minus x squared minus 2y squared, it opens down and it is shifted up. That's going to be helpful when we set up our integral. So for this volume, we're going to take the double integral over our region, which we're going to have to figure out what that is, it's the second function minus the first function. So that'll be like z2 minus z1. The upper one is z2, the lower one is z1. And then of course we're integrating with respect to area. So what does this look like? Double integral over our region of 27 minus x squared minus 2y squared minus 2x squared plus y squared dA. That simplifies to, let's see, 27 minus 3x squared minus 3y squared dA. Oh, and I like that because I see that I can factor out a negative 3 there from the last two terms, which makes my life so much better because I know that x squared plus y squared is r squared. So that allows us to integrate 27 minus r squared, and then dA, remember, is r dr d theta. Ooh, very, very nice. Okay, so now I've got my integrand. Now I just need to figure out what is that region over which we're integrating, meaning where do the r's go and where do the thetas, over which range are the r's and which are the thetas. Well, let's see. In polar coordinates, my thetas, which I will integrate secondly, are going to go from 0 to 2 pi, right? But what about the r values? What does the radius go from? Well, I know it's going to start at 0 because I am sitting here at the pole. I haven't fully graphed this, but you should be able to kind of put that whole graph together if you needed. Right, but what about the upper bound on the r values? Well, taking a look, that would be when those two paraboloids intersect, meaning z1 is equal to z2. So if we set those equal and solve, what does that give us? 3x squared plus 3y squared is equal to 27. Divide by 3. It gives us x squared plus y squared is equal to 9, which I can write as 3 squared. So the radius here is 3. So we're going to be integrating the r's from 0 to 3. While I'm at it, let me go ahead and distribute this r in here. So that gives us an integrand of 27r minus r cubed dr d theta. Integrating with respect to r first gives us 27 over 2 r squared minus, oh guys, I left off a 3. That's minus 3r squared minus 3r cubed now. Okay, so now when we integrate, oh, that's going to be 3/4 r to the 4th, which will evaluate from 0 to 3 and then integrate with respect to theta. Oh gosh, let's see. Evaluating at 0, super simple. Evaluating at 3 gives us, let's see, 9 times 27 is 243 over 2 minus, let's see, 81 times 3 is 243 over 4. Oh, that I can work with. 2 minus 1 is just one of those. That's 243 over 4 d theta. So that is 243 over 4 theta evaluated from 0 to 2 pi. We'll be able to, when we evaluate, of course, at 0, that's easy. At 2 pi, that reduces. And so we end up with 243 over 2, well, 243 pi over 2, and there is our volume. Enjoy!